So this is our belief, or you can say that we know the biomass was precursor of petroleum. So photosynthesis is the green engine of biomass. So all the oxygen in the biomass, it's carbon and hydrogen and oxygen through photosynthesis process. But if we remove the oxygen, we have only hydrogen and carbon, and that is petroleum. So our main challenge is to remove this oxygen from biomass and only have hydrogen and carbon. So it will be similar like the fossil crude. And you know all these biomass and dead animals since billions and millions years before going underground the layers of earth crust. So then pressure and temperature increasing, and this all stuff converted into the fossil crude, which we are drilling nowadays. So we are going to mimic the same process, but we are not going to wait for the millions of years. So we will do in the reactor system to convert such biomass same like into the biocrude. I will tell you in the further slides how we will do this one. So biomass sources, non-food. As I said, we are not talking about the food stuff. So we have plenty of primary residue, secondary residue, and tertiary residue. And we are very lucky in Pakistan. We are a big agricultural country. And we have a lot of crops. And from that crops, we have a lot of residue. You can see in this figure from all the crops. Then we have secondary residue. For example, the bagasse from sugarcane, sawdust, black liquor from pulp and paper industry, slaughterhouse, animal waste, and municipal solid waste. I know from the news it's a big problem in Pakistan, especially in Karachi. We have lot of municipal solid waste, and nobody knows how to handle this one. We can use it in a good way to convert into a good biofuels, but definitely it will take time. It needs research, but we have to think right now how to convert all these things. So we are minimizing the waste and we are getting a good product. Then we have sweet sludge, miscanthus energy crops, jatropha, switchgrass, and microalgae. So we have many agricultural and non-agricultural residues and wastes. And all these biomass and waste, they are different in chemical nature. So if the biomass belongs to crops, then definitely you have cellulose, hemicellulose, and lignin with different percentages. But if it belongs to, for example, the slaughterhouse waste from microalgae and these type of stuff, then we have protein and also the fat. But all these things are good because we are going to convert these cellulose, hemicellulose, lignin, protein, and fat into our biocrude. They are main your monomers, for example, glucose and fructose and protein and the fats, which will convert into the biocrude. So no first generation biofuel. Just imagine if the world airline fleet used 100% biojet fuel from soybean, and soybean is a food product. I am just giving you the scenario. So then you need 322 billion liter of biojet fuel every year. So how you will produce? You will definitely cultivate the soybeans. That is a food commodity. So then you need 575 million hectare for the cultivation of soybean. So I just give you the size of this land. So it will be almost the size of Europe. So to produce 100% biojet fuel, you need a land that is size of Europe to cultivate the soybean, so that you can fulfill the demand of your 100% biojet fuel. So this is from the food. So this is the drawback of the food. You need the land, and enormous amount of land you need it. But if you talk about the algae, that is not the first generation. It's not the food. It's the second generation. And if you need the same amount, 322 billion liter of biojet fuel, so you need only 34,000 square kilometer algae ponds, and it will be size of only a very small country in Europe, that is Belgium. So you can see a huge difference between the land, how much land you need if you are going to grow soybean to produce 322 billion liter of biojet fuel. But if you are using the non-food like algae, you need very small amount of area. You can produce in the raceway ponds like this one, or you can also produce indoor in the photobioreactors. So this is a big difference between the first generation and the second generation, if you are going to supply such kind of biojet fuel. Another bad thing about first generation, if you are producing biodiesel and bioethanol, now people in Europe are also producing biodiesel and bioethanol from second generation from the crop residue. But even though if you are producing biodiesel and bioethanol from second generation feedstocks, even though they are oxygenated fuel, they contain a lot of oxygen in, and oxygen is enemy of engine. We have to remove the oxygen from our fuel. Otherwise, you are going to blend very limited amount. So in filling station, you can see B95, B96. So it means only 5 to 6% biodiesel or bioethanol, rest is your fossil diesel. So if you blend too much, so it will increase the engine NOx emission, stability and storage issues. It's hygroscopic in nature, so it absorbs the moisture from the air, thermal degradation. I'm not going to read all these things, but it's a big problem for the engine, performance related issues, and also some technical challenges. If you are going to use your diesel engine in aeroplanes, in the aviation industry, so you can see the freezing point of biodiesel is almost close to zero. And at cruise altitude, it must remain fluid. But the original jet fuel, it's minus 40. So you can't use 100% biodiesel in your aeroplanes only because of this property, because it's going to freeze at 0 degree. So that's why you blend 20%. If you are going to increase the blending ratio, you have to change your engine modification. Because sometimes you can see the instruction manual from the car industry, they will say only these type of fuels you can use in our BMW or in Toyota, otherwise you will face a problem if you are going further blend. So that's why this is a big issue with the biodiesel and bioethanol. You are not allowed to increase the blending ratio. You cannot use 100%. If you are going to use 100%, you have to modify your engine. Now the main conversion option for the biomass to secondary energy carrier. We have two main categories. So thermochemical conversion, then biochemical. Then we have the mechanical. So you extraction of the oil from the crops, esterification, biodiesel, transportation fuel. From biochemical conversion, you have fermentation, your distillation, then you use produce the bioethanol, transportation fuel. Similarly, biogas through digestion process, gas engine, you can also use as a transportation fuel, or you can also burn it and generate the electricity. Thermochemical, by its name, it's a high temperature pressure process. For example, combustion, very high temperature, gasification, and pyrolysis. So you are producing from combustion the steam, then steam turbine, you produce heat and also electricity. Similarly, in case of gasification, you are producing some gases, you do some Fischer-Tropsch, convert into some liquid fuels, and you can use also the hydrogen in the fuel cell. In pyrolysis and liquefaction, you are producing also gas and bio oil, then upgrading, because this bio oil is not able to use directly into the internal combustion engine or in the diesel engine. So that's why you need the upgrading and convert into diesel, and you can use in the transportation fuel. So these are the main conversion options, how to convert biomass into energy carriers. But before starting any technology, there are some key issues from all the parts of the technology. For example, feedstocks, technologies, then products. In feedstock, cost is very important. Either your feedstock is cheap or expensive, its quality, is it able to convert into the oil or into bioethanol or biodiesel, then also the availability from where you are getting, so all the transportation cost and location. Then if you are talking about the technologies, what will be the status of technology? It's apex and capital cost, operating cost, then yield, efficiency, scale, and how many byproducts you are producing. If you are producing the bioethanols, then what will be your byproducts to optimize the process, to make it more and more cheap. Then you are getting product. So what's the value of your product? Is any need or demand in the market, and then competing routes. So if you are producing biodiesel, so maybe another company is also producing the biodiesel or bioethanol. So what will be the competing routes? Then quality specification, is your biodiesel is according to the international standards? Then green credits, is it really and truly renewable and sustainable? So all these issues we have to address before starting any technology, any feedstock, and any product before making it. Then fuel criteria. So when you produce any sustainable and renewable biofuel, especially the liquid biofuel, then you have to check its suitability. What will be the physical and chemical property of that fuel? What will be the emissions when you will burn it? What will be the performance of your engine after using this kind of biofuel? And another thing is sustainability. Is it really sustainable? And the cost, and also the supply, because sometimes you have to supply a large amount of biofuel to the companies and to the industries. So supply and cost, and also the net CO2 saving, and food versus fuel. And the last thing is industrial capability. So is your fuel is really capable to put as a drop-in fuel in the already existing infrastructure, and also the life cycle analysis of your biofuel. So this is the fuel criteria. If you are going to produce the biofuel, we have to think about all these factors: suitability, sustainability, and industrial capability before starting any process for the production of biofuel. So now come to the point of our hydrothermal liquefaction process. So it's a high temperature and pressure process. So very effective technology. So we can efficiently valorize different type of wet biomass feedstock. We can also use the dry one, but if we are using the dry one, we have to put the water by ourselves. So we can use any lignocellulosic biomass, algae, organic waste, animal waste, sewage sludge, any kind of thing. If it's wet, if it's dry, it doesn't matter. So we perform this liquefaction process at supercritical condition of water. At supercritical condition, that is more than 374 degrees C temperature and almost more than 220 bar pressure, water behaves in a very different way. So it changes its properties. So at high temperature, at supercritical condition, due to the low density of water and due to high ionic product, it will prefer the ionic reaction rather than the free radical reaction. So we will get more and more liquid biocrude oil and very less amount of char. And similarly, at supercritical condition, due to very low dielectric constant, most of the organics will dissolve in the water. So that's the beauty of the water at supercritical condition. So that's why we are working at high temperature and pressure to convert more of the biomass into our biocrude. As I said, our main product is biocrude, then solid residue, then water soluble fraction. In that water soluble, we have short chain alcohols like methanol, ethanol, some acids like acetone. And we also have the gases, but more than 90% gas will be CO2, because maximum oxygen in our biomass we convert into CO2. So that is main objective, to remove maximum oxygen from the biomass, convert into the CO2. Then rest will be only your carbon and hydrogen. And that is the main building blocks of your any fuel. So you can see in the picture, we can use lot of biomass containing protein, carbohydrate, lignin, and all these things. Then we make an ideal composition of the HTL reactor feed. You can say it's a slurry. So our main ratio is more than 75% water and 25 to 20% our dry matter contents. So we convert into our reactor at high temperature and pressure. Then we get our gas phase, our oil, our water, our biochar. So gas is mostly CO2, as I said. Our water contain soluble fraction. Biochar, we can use this one as a fertilizer because it contains a lot of potassium nitrogen and phosphorus, and that is good for the plants as a fertilizer. And that bio oil or bio crude is not able to use directly. So that's why we need the upgrading. So we add hydrogen more to remove the rest of the oxygen, maybe 5 to 6% left over. Then we convert into our main upgraded bio oil. Then we make this pentagon figure or graph you can see. So the red one is our HTL oil, and the red one is the diesel, and the green one is our HTL oil. So in this pentagon, we have to minimize 4 corner, and 1 corner we have to increase. So we have to increase the heating value, minimize the viscosity, minimize the sulfur contents, minimize the oxygen, and minimize the density. Then our oil will be very close to our diesel, our fossil diesel, which we are nowadays using in our car engine. So this upgraded oil we can convert into our diesel, same like which we are using nowadays. But this is our, you can say that objective and our task to reduce the oxygen content, density, viscosity, and sulfur. Then we can meet the standard of the current diesel specifications. So in the lab, we have all the instrument from lab scale to pilot scale. So for example, we take straw. It's a crop residue from wheat straw, from rice straw. We make the slurry, almost 7 grams we put into the reactor. We connect all our capillaries and all our pressure transducer. Then we do the leak test. Then we connect all our transducer and thermocouples. Then we send into our sand bath. So this is our lab scale result, lab scale setup. So we tried all different biomass to see how much we can convert into the oil product. So this is preheated. We just hang our reactor here and shaking it. And then after 15 minutes of retention time, we just remove it. And then we do all this process, you can see. So this is liquefaction. We collect the gas product. We do the gas analysis, how much gas we are getting. Then the collected product, you can see it will be like this one, a black liquid. It contains water, it contains solid, it contains oil. Then we do the filtration and we wash our reactor system with acetone, because acetone is very good solvent to dissolve all the oil and clean all the stuff. And then we remove the solid phase, then drying. So this is our solid phase. You can see very small amount of solid phase. Then we use the rotary evaporator. Then we have oil and water phase. Through rotary evaporator, we remove all the acetone which we added by ourselves for cleaning of our system. Then we use diethyl ether. Then we remove all the water phase here, and we have all the oil phase. So from biomass, we are getting the gas, solid, oil, and water. So we separate this one on the lab scale. We tried a lot of biomass feedstocks, barley straw, organic waste, then microalgae, aspen wood, then municipal solid waste, and grasses and wheat straw and lignin, and all these things we publish. So we tried a lot of biomass feedstock, because we are, as I said, we are working since almost more than 12 years in this technology. So that's why we have also the lab skill setup. We have a batch reactor.